Good morning, students. This is Topic 7, Video B, Ionic Size. We have learned to use fundamental electrostatic arguments to rationalize atomic size. But what about ions? Can we use the same logic to estimate sizes of ions? After all, ions are nothing more than charged atoms. Consider the sodium atom and the sodium ion. Here are the electron configurations of the atom and the corresponding ion. Recall that the 2s and 2p electrons are in a single shell, shown in the figure as one concentric circle with 8 electrons. Notice that the ion has one fewer shell than the atom. We would predict then that the sodium ion would be smaller than the sodium atom, and we would be right. Cations are always smaller than the atoms they come from. What about anions? Let's consider the fluorine atom and the fluoride ion. Here are the electron configurations. The atom and ion have the same shells and the same positive nuclear charge, that is the same number of protons, so the only difference is the number of electrons. The anion has more electronic repulsions, so we would expect the fluoride ion to be larger than fluorine. Again, we would be right. Anions are always larger than the atoms they come from. Let's summarize by visualizing the sizes of some atoms and their ions. Cations are always smaller than the atoms they come from, and anions are always larger than the atoms they come from. Pause here and make sure you can explain all the trends you see in this table. Let's practice by thinking about a new idea. Isoelectronic ions and atoms have the same number of electrons. Pause the video here and convince yourself the statement is true by filling in the table shown below. Here are the solutions. All ions are isoelectronic. Notice that some atoms gain electrons and some lose electrons to create the isoelectronic ions that have the configuration of neon. Now try to arrange the isoelectronic species in order of decreasing radii, that is, from largest to smallest. Pause here and write the answer in your notebook. Here's the trend. Since the number of electrons are the same in each ion, the radius is determined by the number of protons, according to Coulomb's law. The nucleus of the ion with the greatest number of protons, that is the Al3+, has the largest pull on the electrons and is therefore the smallest ion. Sometimes, students think that because sodium, magnesium, and aluminum are in period 3, they should be bigger. But remember, these are isoelectronic because they have lost different numbers of electrons.